Hello, I'm going to talk about exponential functions. This is new to us. An exponential function is a function that the input or the x variable is in the exponent. So here in my second sentence, I give you a little taste of what it looks like. In function notation, f of x equals a to the x, where a would be a number and x would be still a variable, or if you like it in the xy notation, y equals a to the x. Okay. A is really going to represent how this thing is going to change. And a little note here that if a is bigger than 1, then it's going to be a function that increases, because basically you're going to be multiplying over and over by a number bigger than 1. So it's going to grow. Whereas if a is less than 1, it's actually going to cause the function to get smaller because you'll be taking a portion of what is already there. So you'll be multiplying basically by a fraction over and over, which would get it smaller and smaller. A little bit more detail to the function. We can put a multiplier in front, so c times a to the x. In this case, basically, the c would be like where the function would start as far as the starting value. So if you think of it as an x-y combination, basically if you plugged in 0 for x, no matter what a is, anything to the 0 is 1, so you would get c. We'll see this in some examples here in a moment. But you can kind of think of as a being a rate of change or some type of multiplying factor, where c is a starting amount, what this function would actually start looking at if we're looking at a y-intercept. So let's look at a couple of examples here and real use. Let me see if I can do this a little bit better so that it's not my face still showing down here. Okay, so here's a example from Khan Academy. It says Pavlo invests some money into a bank account. Basically here we have T, which is how long the money is going to be in the bank in months, and M of T, which is an output similar to a Y, is the amount of money that would be in the account after T months. And here is what the function actually looks like. They're giving us this. So one of the things they're asking us is the amount of money in the account going to grow or shrink? Well, let's look at a couple of things first. First of all, we see this multiplier times the exponential part, this 1,000. This 1,000 would be how much money he's actually putting in the bank. Okay, so that's how much money he has when he starts. Over here, the 1.01 is how it's going to change. Now, first of all, that number is bigger than 1, so that means his money is going to grow. He's going to have more money in the future than he does now. So it's going to grow. But a little bit more interpretation of that 1.01. Let's bring it up a little bit here. I've got that's the a value. But you can think about the 1.01 similar to 101%. So what that means is he's keeping the original 100% of his money that he started with, and he's adding an additional 1% to it. So the multiplying factor here is 1.01 or 101%. But what's actually happening is he's gaining 1% per month. The 1 out front means he's keeping the original amount, because if you multiply by 1, you get the same thing back. But increasing that by 0.01 is increasing it by 1%. So basically every month he is gaining 1% of whatever he had the previous month. So it's going to grow by a factor of 1.01, which we can also interpret as 1% growth. Okay. Let's go to another example here. So in this particular one, we're going to see the same situation, but it's going to be a little bit more complicated as well. So here we're going to worry about time and how that time could be adjusted. In the previous example, we just had t up here, okay, which meant in this case, if t is in years, we just plug in the number of years and it would be pretty straightforward. Well, we still got something simple where we can plug stuff in. Basically it says what we got here. Howard starts studying how the number of branches on his tree grows over time. Okay, so T is years, so number of years, and NT, which is the output, similar to a Y, is how many branches after that time. So right here we've got 38, which corresponds to the C in the original problem. So that means he started at, when he started measuring this tree, with 38 branches. Okay, 9/5 is the multiplying factor here, or the ratio, and we'll look at the part up here in a second, but let's just kind of look at what the question is. It says Howard's tree gains 4/5 more branches every blank years. So let's interpret this. Just like the previous one where there was 1.01 here, that one part meant the original part was being kept. Then the 0.01, anything beyond 1, is how much he's gaining. So if we took the 9/5 and we subtracted 1, okay, 9/5 minus 1, we'd have 4/5. So really, this is talking about increasing it by 4/5 every time. Okay, multiplying by 9/5, which increases it by 4/5. Okay, so what I've got a little explanation down here. That means he's keeping the original, which is 100%, plus he's tacking on an extra 4/5, which is 80%. Now, to handle this question here, we need to think about what's happening to the T up here, because we'd plug in a number of years, and whatever that is going to get divided by 7.3. So for this thing to actually be 9/5 here after the exponent is applied, if we raise 9/5 to something and we get 9/5 back, this up here would have to be 1, the whole exponent part, T over 7.3. So what we need to do is plug in something that would make this 1. Okay? And the only thing you could plug in for T that would make T over 7.31 would be 7.3. So basically what we've got here is we got that if we plugged in 7.3, that we would get that. So Howard's tree gains 4/5 or 80% more branches every 7.3 years. Okay? Or gains 80%, however you want to perceive that. So down here, just to kind of show you that, I took the function notation, plugged in the 7.3, the exponent becomes 1, and if we do this calculation, we get 68.4. Well, if you want to take 38 and figure out what 4/5 of it is, and then add it to 38, you should get this 68.4 over here. So you can try that. Okay? But everything works out very clearly there. So if you've got some type of division or multiplication up here possibly, that's adjusting how that time is being handled. T is still the number of years, but it's going to take more years with this divisor to actually have this multiplying factor fully applied. Let's see if we got another example down here. Yes. So here, I think this is my last example, but we also want to write an exponential function from a description. So here it says we have medicine in a petri dish, and the number of bacteria remaining in the dish decreases rapidly. So basically we've got some bacteria in a dish, and we're going to put some medicine in there, and it's going to start killing off the bacteria. So let's see what it says here. It says the population loses 1/4 of its size every 44 seconds. Okay. So that's two good pieces of information. It also says down here that when we start, there's 11,880 bacteria. So we're going to try and write this function in some type of starting amount C, which is obviously 11,880, times some rate, A, which we'll talk about in a second. And then it looks like we may have to adjust for time since it's talking about every 44 seconds. So it loses 1/4 of its size every 44 seconds. So we need to make two adjustments here when we plug this in. Okay. First of all, we're losing 1/4. So if you take a look at this part I'm kind of focusing on right here, we have the original amount minus 1/4 would leave us with 3/4. So basically we're keeping 3/4 of what we originally had. Okay, we're losing 1/4 of the original bacteria, so we're keeping 3/4 of it. Okay, basically we're losing 25%, so we're keeping 75%. You can look at that in decimals, but I will leave it as 3/4. So this multiplying rate in here is 3/4. So right now we have the starting amount 11,880, and we have the multiplying rate here as 3/4. And just like in the previous example, it takes 44 seconds for this to happen. So for this entire 3/4 to happen, we'd need 44 seconds. So we'd need t to be 44, and we need something to happen to the exponent to make it 1. So that's why I have it divided by 44. So if I put in 44, and I divide by 44, okay, I would get 1, and then I would have 3/4 of the original starting amount. So that would make the function. Okay, it's not so easy to do, but take some time to work with it and think about it, and let me know if you have questions. All right, thank you.